We're going to talk a little bit more about increasing and decreasing. Actually, there's nothing more to say really about it. I just want to do a couple more examples that are harder than the ones that we did last time. Last time we just did polynomials. A couple more, actually, literally a couple, two more examples of more complicated functions. First, I will refresh your memory on the procedure. All right, here's the procedure. Step 1, find the critical numbers. These are the x values where f prime of x equals 0 or f prime of x does not exist. Second step, make a little chart and label the points. The points to label on the chart are the critical numbers that you found in the first step. And lastly, you plug values into the derivative to find the signs of the derivative on the intervals in between the critical numbers that you put on the chart. I hope you remember the examples we did last time. Let's just do a couple more. All right, first example of our couple more. What makes this more interesting or more difficult than the ones we did last time is it's not just a polynomial, it's this quotient thing. So when you take the derivative, you're going to have to use the quotient rule, and then you're going to have to do slightly more complicated things when it comes to finding the critical numbers. Anyway, we begin by taking the derivative, f prime of x. This is like step 0. This is what you have to do in order to find the critical numbers. F prime of x. I gotta use the quotient rule, so I'm gonna go bottom times the derivative of the top minus top times the derivative of the bottom divided by the bottom square. All right, bottom is this times derivative of the top is 2 minus the top 2x minus 1 times derivative of the bottom, which is 1, all divided by the bottom squared, which is like that. All right, like I said, I want to simplify this as much as possible, because we're going to have to use this over and over again in the next steps. So what can we do? The bottom, I suppose you could multiply out the bottom, but actually there's no sense in doing that. That's not going to make it simpler. That will make it more complicated. On the top, I'm going to distribute and recombine those things. So distribute this here on the 2. I get 2x minus 10, right? And then I see minus 2x minus 1 times 1. This doesn't really matter, so I guess it's still like that. Then I get 2x minus 10 minus 2x plus 1. I distribute the minus sign right there. Same business on the bottom. And then finally, what do we get? 2x and minus 2x will cancel. Isn't that nice? And then negative 10 plus 1 is negative 9 over x minus 5 squared. Okay, this is the derivative, f prime of x. All right. We need to find, and that's as simple as that's going to get, we need to find the critical numbers. That is, when is this equal to 0? And when does this not exist? Let's try it. Okay, first I'm going to look for points where f prime of x equals 0. So you set this equal to 0 and solve for x. Minus 9 over x minus 5 squared equals 0, and we solve for x. What do we do to solve for x? When you have a fraction, you multiply the denominators across. So I'm going to multiply this over there. It'll say minus 9 equals 0 times x minus 5 squared. This, of course, is 0. Minus 9 equals 0. What does that mean? Okay, minus 9 does not equal 0, right? That means this is impossible because it's just straight up false, which means all of these other things are impossible. Your interpretation of this, if you ever see this when you're trying to solve for x, your interpretation should be no such x exists. That is, there is no time, there is no x when f prime of x equals 0. So my interpretation of that is, so f prime of x is never 0. All right. We should also check, when does the derivative not exist? So I'm also going to check f prime does not exist. Now for this, you have to look at this formula here. This is f prime, and ask yourself, when could that thing fail to exist? Is it possible that this could fail to exist for some values of x? You should be looking, as usual, for zeros in the denominator. That's what will mess up this formula. And it is possible for the denominator to equal 0. So for this, in this case, I'm going to look at denominator equals 0, right? In this case, you know, you can just look at that and probably guess what is the value of x, which makes the denominator 0. If you're having a hard time guessing, though, you can just set the denominator equal to 0 and then solve for x. I would take the square root on both sides to get rid of the squaring. It'll just say x minus 5 equals 0. When you take the square root, really it's like plus or minus 0, but plus or minus 0 is the same as 0. Anyway, x equals 5. Probably could have guessed that from there. Okay, so x equals 5 is a critical number. We get this one critical number from here and no critical numbers from here. So our only critical number is x equal 5. Let's make the chart. All right, I mark off the point x equal 5 as our only critical number, and this is a point at which the derivative does not exist. All right? Doesn't really matter if this, some critical numbers, the derivative will be 0. Sometimes it will not exist. What you care about is these regions over here and over here. You want to decide, is the derivative positive or negative? So I'm going to choose some value. Choose your favorite number greater than 5 and your favorite number less than 5. For a number greater than 5, I'll just go with 6. Plug it into f prime of x. I get negative 9 divided by 6 minus 5 squared. All right? Is that positive or negative? Actually, the bottom, you will notice, the bottom is always positive, isn't it? Because it's something squared. So this, whatever it is, actually it's just 1. But anyway, this is negative, right? It's negative 9 here. So f prime of 6 is negative, which means over here I'm going to write a big old minus sign. That's a minus sign. And then what about your favorite number less than 5? I will choose 0. I always choose 0 if I can. That's just my lifestyle. Minus 9 over, that's how I roll. Like that, right? Again, the denominator is positive, the numerator is negative, and so this will be negative, like so. All right? That's all there is to it. What's the answer? You check out the chart and you just say, where is it positive, where is it negative? This one is always negative, so I'm going to say f is decreasing on the interval minus infinity to 5 and 5 to infinity. It's actually, you may be tempted to just say it's always decreasing. It's, technically speaking, it is not decreasing right at x equal 5 because the function doesn't even exist there. There's no derivative at all there. So it is not decreasing at that point, but it is decreasing everywhere else. It is decreasing for on these two intervals. You can always check your answer with these. If you have a fancy graphing calculator or just a computer, you can graph these things on a computer and check yourself. Here's a graph of the original function, f of x equal 2x minus 1 divided by x minus 5. And I will have you notice it is indeed decreasing everywhere except right at x equals 5 where the function doesn't even exist. All right. That was the first example. Here comes the second one. How about same question? Where is it increasing and decreasing? F of x equals x times e to the negative 3x. All right. This one is harder for different reasons because we have an exponential function in there. So you got to work a little harder when it comes to finding the critical numbers. All right. Let's not think too hard about it. We begin by taking the derivative. In order to find the critical numbers, we have to take the derivative and then simplify as much as we can. When I do the derivative here, what are we going to do for the rules? What do we have to use here? First of all, it is a product right there. We have x times e to the minus 3x. So I'm going to do the product rule. That will be the first thing times derivative of the second thing plus the second thing times derivative of the first thing. You also have to remember how to find the derivative of an exponential e to some power. We'll do that when we get to it, I guess. The product rule, I go the first thing like it is, which is x, times the derivative of the second thing. Okay, now is when we have to take the derivative of the second part. I hope you remember the derivative of e to the x is e to the x. Look back in your notes if you forgot about that. So when I take the derivative of this, I get the same thing again. But then because it's not just x up here, it's some more complicated thing, I got to do the chain rule. I multiply times the derivative of the inside, which is negative 3. All right? This is the first half of the product rule. The first thing times the derivative of the second thing, and then I go plus the second thing times the derivative of the first thing, which is 1. All right? This is my derivative. I want to simplify this as much as possible. This can be a little tricky sometimes, but what I have here, let me just rewrite this. I'll sort of bring these constants to the front. This is negative 3x e to the minus 3x, and then plus, this constant doesn't matter. It's just e to the minus 3x. All right. One thing I want to do additionally to simplify this is I have two things added together. Each of them has e to the minus 3x on it, so I'm going to factor out the e part. Makes e to the minus 3x, and then negative 3x plus 1. All right? This is as simplified as that is going to get. So this is f prime of x. This is the thing that we're going to base the rest of the problem on. I might as well erase at this point. All right, we got to find the critical number. So we look for, first of all, when is f prime of x equal to 0? You set this equals 0. Right? And solve for x if you can. What can we do with this? I have two things that are multiplied to be 0. That means either this one is 0 or this one is 0. So, okay. This equals 0, or minus 3x plus 1 equals 0. And now we solve each for x. This one is easy enough to solve for x. You add the 3x over there. It says 1 equals 3x. Divide by 3. X is 1/3. All right? What about this one over here? E to the minus 3x equals 0. This is a little tricky to solve. You could solve this by taking the log on both sides, but actually the log of 0 is not defined. If you try that on your calculator, you'll get some error. That's because there are no solutions to this. The simple fact, the slogan that I would like you to remember about this, I hope you remember the graph of an exponential function typically looks like this, right? And you will notice an exponential function such as this is always positive and never 0, right? This exponential function is never 0 and it's always positive. It's always up there. So this right here gives me no solutions from this part, because it is impossible for any exponential function to equal 0. So e to the minus 3x equals 0 has no solution. So from this part we get nothing. From this part we do get a critical number over here. All right, let me just write in words what I said, because this is important even in other contexts. Later on in this problem we're going to use this fact again. E to the any power is always positive, never 0. All right, so that's why when I see this equaling 0, you just can't, there are no solutions to that, because this is impossible. That one is possible, you get a critical number. Later on, actually in this problem, we're going to use the fact that it's always positive. You'll see in a moment. Anyway, we got one critical number right here, so I'm going to make my chart. Oh, I forgot to say, you also need to check when the derivative does not exist. When does this not exist? The answer is this always exists. There's no denominator, which might equal 0 here. And so there is no critical number because the derivative does not exist. Okay, so our only critical number was 1/3. I'm going to make my chart here. I mark off the number 1/3. And the derivative here is 0 right there. Otherwise, I need to check over here and over here. Is it positive or negative? Positive or negative. So choose your favorite number greater than 1/3. How about 1? I do f prime of 1 is plug 1 over here. E to the minus 3 times 1 times negative 3 times 1 plus 1. What is this? This is e to the minus 3 times, this is negative 3 plus 1 is negative 2. Is that positive or negative? Now, of course, you can plug this into your calculator if you want to, but on our tests and quizzes or whatever, you're not going to be able to use a calculator. It don't matter. Is that positive or negative? Well, this is negative, certainly. What about that? E to the minus 3, is that positive or negative? Remember what I said just a moment ago. E to any power is always positive and never 0. So what we have here is a positive times a negative, which is negative. So over here, the function is, the derivative is negative. All right? E to any power is always positive, never 0. Doesn't matter what the exponent is, it's always positive. All right. Your favorite number less than 1/3? Let's do 0. I like 0. E to the minus 3 times 0 times negative 3 times 0 plus 1. What do we got here? This is e to the 0. Actually, that equals 1 times 1, isn't it? This all just equals 1. Okay, that's positive. And that means we got a plus here. Okay, that's it, really. Can we just say the answer? Maybe I'll write it up here. F is increasing on the interval minus infinity to 1/3. Decreasing on the interval 1/3 to infinity. And as we did in the previous example, you can check this answer by looking at a graph on your computer, on your calculator. Check it out. Remember to graph the original function, which was x e to the minus 3x. And you do see, indeed, the function is increasing on minus infinity to a third, and it is decreasing on 1/3 to infinity. Great job.